In this video, we're going to consider the covariance matrix and which one is the best to use. In the analysis we've used here, first, we've used compound symmetry, which gives us a single estimate of the covariance. And that was down here under the estimate of the covariance parameters. In order to determine the fit of the model, we use these information criteria. Really, they're all essentially giving the same kind of information. They just calculate things a little bit differently. Aki-Ike's information criteria is a popular one that's often reported. And the objective is to make this number as small as possible. This is a pretty big number, and unfortunately, there is no relative number. Like you think of 2 standard deviations or 2 standard errors, a z-test out that, well, 2 is kind of a constant number. There is no constant number in these measures. It's simply smaller is better. And you are going to want to have kind of a relative, as the model gets more complex, you want to use the simplest model that has the best fit. If we knock this down to 4603 with a very complex model, we would stick to the current one because that's just not enough improvement. It's kind of a subjective feel for how much is enough. So here we have used it. Let's go in, and these are years, and the characteristic of years is that as we go down, we would expect years closer to each other to be more correlated, the data to be correlated higher than years further apart. For example, refractive error would be more correlated if you measured it 1 year and the next rather than 1 year and 5 years next. And to do that kind of a covariance matrix, where we're going to adjust for the change, this incremental change in year, where we expect that kind of pattern rather than the same across all years, no matter how far apart they are, we're going to use AR1, autoregressive coefficient. Now, this, again, it picks one that's across good for all ethnicities. We could go to this model, which calculates the one for each pair of years plus the ethnicity. It's just a more complex number. So we're going to go with the simpler model. So I'm going to pick that, continue. Everything else is the same. We'll see what we get. So to remind ourselves, the Aki-Ike was 4604, and the new one is 3882 or 3886. So that is a big difference. So we dropped by 600 points almost. So that's a big improvement. This model is a better fit. Our estimate now is 0.40 as opposed to 0.19. So that estimate's doubled, but it's a better fit across the board. Let's do it one more time. Let's try that heterogeneous one and see if that gets us any better. or 3663 compared to 3886. 886. Well, that's, that's not, that's a little bit better of a comparison of one. It's not a huge, as big of improvement, but it's definitely an improvement. And now our covariance, we get, so when we calculate our estimates, we use a different estimate for each year. Notice down here, years 6 and 5, we have a much bigger estimate of the underlying covariance, and that's due to the fact that we didn't have a lot of subjects down here. Although we didn't have many up here either, and it didn't seem to affect it as bad. They happened to be closer together. But after years of being myopic, you have a bigger problem. So we would take the square root of these and apply it differently to each year. And so those are ways of handling the different covariance matrix. And it's just a trial and error to find the one that fits the best.